Applications of parabolas. Parabolas have a really cool reflective property that anything coming from the focus will reflect straight out directly perpendicular. Oh, I have to sneeze, sorry. Perpendicular to the latus rectum. So where this is used is things like in lights. The light is placed at the focus of a parabolic mirror. The light will be reflected in parallel rays. So you can kind of see like a car lamp, headlamp. Wherever the bulb is placed, it needs to be placed at the focus so that the reflection reflects straight out. No matter what angle it's going at, it's going to reflect straight out there. Satellite dishes are the same kind of idea. That receiver is at the focus of the parabola so that that signal is reflected straight where it needs to go. A little bit here about eccentricity, just kind of summarizing. If E is 0, then you have a circle because C is 0. If E is between 0 and 1, you have an ellipse. The closer it is to 0 means the foci are closer and the ellipse is more circular. So the closer to 0 you have, the ellipse is more circular. The closer to 1, the ellipse would be more oval. A parabola has E equal to 1. A hyperbola will have E greater than 1. Remember that picture where we had calculated all those E's? It's because C is bigger than A in a hyperbola. Okay? Let's look at an application of the parabola using that reflective property that a parabolic surface has. Obviously, in these situations, we are talking about a three-dimensional parabolic surface. These are sometimes called paraboloids, where it's parabolic, sort of rotated around. But still, the property still holds that for each cross section of that parabola, it will still have that reflective property. Let's talk about this. I want to draw a picture here. We have a diameter of 8 inches and a depth of 1 inch. So let's draw this. Oh shoot, that doesn't look super good. It's pretty narrow, or not very deep compared to its width, right? That's why I was trying to kind of draw this parabola, where this is 8 and this is 1. Okay, this would be the vertex here. We can choose for that vertex to be at 0, 0. And if we wanted, just because it's easier and what we're kind of used to, let's actually rotate this, because we can choose. It's our picture. We can kind of choose. I'm actually going to draw this opening up, this parabola opening up, because I can. Just like I can set the origin to be where I want it to be, I can orient this the way I want it to. So now I'm saying my axes are here. Okay. I don't know exactly where my focus is on this, but it's going to be somewhere in here, probably. We'll see. Actually, I don't want to assume that. It could be outside. Let me erase that. Here's what I do know. With a vertex of 0, 0 and it opening up, I am looking at x minus h squared equaling 4p times y minus k, where h and k are both 0. So let's simplify that to this. X squared is equal to 4py. This point, this is 1 inch depth, right? This ordered pair would be 1, or would be what? 0, 1. This ordered pair right here, if this is 8 inches wide, it's 4 inches from the center out, right? So the ordered pair at this point would be 4, 1. The reason I care about that is because only these points down here are actually on this parabola, right? The points across the top here are not on the parabola. So I know that 4, 1, negative 4, 1, and 0, 0 are on the parabola. Those are the only points that I know of on the parabola. I am going to use that fact that when x is 4, y is equal to 1 to find p. 16 equals 4p, so p is equal to 4. The question asks how far from the vertex should the light bulb be placed. P is 4 is the distance from the vertex to the focus, and that is out at 4 inches. So the bulb should be placed 4 inches from the vertex. And we could say above, below, right, or left. We could rotate this any way. It's not going to change the fact that P will be 4. This is critical in design of things that you need this reflective property for. Like, you need a flashlight to aim a certain way, right? You need the beam to go a certain way. You need a headlight on a car to go a certain direction. You need a satellite dish to be pointed toward the satellite, so to receive that signal. So that is important. It's an important idea that we're using the reflective property of a pair of parabolic surfaces. The last thing we're going to talk about with conic sections is how to make sure we know when we have which type of conic section. A parabola occurs when either A or C is 0 in this general form. This would be the general form of a conic section. You only want either x squared or y squared, not both. So if you have a y squared, so C is not 0, you need A to be 0. One or the other has to be 0 to make that squared term disappear. A circle occurs when A is equal to C. You need, oh yeah, that's good. They both have to be positive or both negative. They have to be equal to each other. An ellipse occurs when A is not equal to C, but they are the same sign. They have to both be positive or both be negative. If they're both negative, you would just have to divide both sides of this equation by a -1 to get that positive that you wanted to have. A hyperbola would require A and C to have opposite signs. When I say sign here, I'm talking about positive or negative. One positive, one negative on the hyperbola. That's the only way you're going to get that subtraction between the two squared terms. Okay, notice we are completely focusing on just the x squared and the y squared terms, right? That is how you know is what is happening with the x squared and the y squared term. This first one has to be a parabola. There's only x squared, not y squared. Part B, actually, I'm going to give you a second to try to find these. Go ahead, pause the video and see if you can figure out what B, C, and D are based on what we said above. Hopefully you paused the video and now you've unpaused. In part B here, we have both x squared and y squared, so we know we do not have a parabola. The numbers are not equal, but they are the same sign. So it's an ellipse. This is the same. The -3 and the -13. I'm looking at the coefficients on x squared and y squared. That's still an ellipse. We would just have to divide both sides of this by -1 to make them both positive. And last, -4 and -10 have opposite signs. Here they're the same, right? They're both negative. So this would be a hyperbola. We need to be able to determine what type of conic section we're given so that we know the approach to take, right? So that we have a general idea of what we're graphing. That's kind of been the general theme this whole semester is you want to recognize a parabola. You want to recognize a line. You want to recognize a general polynomial. You want to recognize a rational function, square roots, and so on, right? The same thing holds for conic sections. Even though these aren't necessarily functions, we still want to be able to recognize what type of conic section it is. That's why we spent some time classifying this here. Keep working on these conic sections. There's a lot to unpack here, a lot of things to mess up because there's a lot of similarities in them. So somehow try to keep that straight in your brain. I will post a document. I think I have a document that sort of summarizes these, and I will post that in D2L for you.